start the recording, and I share. And I share presentation with you. Okay. Please let me know. Can you see the presentation? Is this visible for you?
Yes, it is.
Oh, 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 it can be seen. I think somebody cannot see the presentation. Please let me check.
Actually, for me, it's kind of black screen, so there is no anything.
Okay. Don't worry. I will check the solution. Can you see now or not? Can you see the
Actually,
presentation?
no. So, what about the other
Okay.
participants? They can see the screen, or this is the problem with me?
Okay. Um, mm, Let me check other options. I can share my whole screen to you. Can you see now? Okay. It seems that it's clear to you, yeah?
Yeah, now I can see it. Now I can see it.
Okay.
Thank you so much.
Okay, thank you. Okay, we can start now. Well, please let me start with say something about the ABAQUS program, and its overview and its history. ABAQUS is a software suite for finite element analysis and computer-aided engineering, which is suitable to simulate and analysis of a wide range of engineering problems, whether in mechanical, whether in mechanical or civil fields, or biomechanical, chemistry, and something like that. It's a well-known FE commercial package which is very famous all around the world. I have to say that the first version of the program were released in 1978, while before that, in 1968, the first version of Nasran, MSc Nasran, was published in the US, and after 4 years, the Analysis System Corporation in that country released the new version of ANSYS program. In fact, the ABAQUS program is not the first FE commercial package all around the world, but we can say that it's almost the best and well-known program in engineering fields. Do you know my voice clearly? Please let me know if you can hear my voice clearly. No. Okay. Okay. No problem. Uh, I think it's better if I do you hear me? Please let me know if you hear my voice clearly. I think somebody in the class cannot hear my voice. Oh yeah, it may be possible. Yeah. Okay, don't worry. The class will be recorded, and please ensure that you don't miss the class anyway. Okay, okay. We can go ahead. Please note that the name and the logo of the program uh, is about the basis of computations. It's about abacus, which means that the basics of calculation. So we found that the program and its originality is about computation. Abacus product, the Abacus product suite consists of several core software products and programs, which I will talk about them in this session. First of all, I have noted that there are three different steps to define a complete simulation in Abacus program. The first step is a pre-processing, in which we have to model our problem. I mean that at this stage, we have to define the geometry, material model, loading protocol, boundary conditions, interactions, topology optimization, and something like that. Please note that at this stage, we have to be care about whatever we define in the program, because the next steps will be based on the items which we define at this stage. In addition, we have to say that at this stage, the program will never help the users to define whatever they want. I mean, it's the user who is responsible to define a correct problem in the software. After that, at the second stage, which is processing, the program starts to form and solve the system of equations by the solvers which we mentioned during the modeling procedure. At this stage, the user cannot see whatever happens during the analysis, and he have to be patient to finish the progress of analysis. After the analysis will be finished, the results are ready to be extracted by the user. At this stage, which we name it post-processing stage, results and variables are are available to be extracted and checked by the user, and we have to be concerned about the variables, about each variable can be extracted by the specific menus and tools. In this session, in the course, I think at the next session, I say something about how we can, whatever we have to do to define a model and submit it for the analysis, and then extract the results in a basic and simple problem. Now, I have to say some tips about a modeling procedure. First of all, we have to define a discretized geometry in our model. I mean, we have to draw or import a new geometry to the program, and then discretize the geometry and divide it into some parts which we name it elements, nodes, integration points, and section points. As you can see in the figure at the right side of the slide, this portion of the plate is a continuum definition, which means that all masses and volumes are mixed with each other, together, but during the discretization procedure, we have to separate masses and name it nodes, and volumes and name them elements. Please note that the procedure names discretization and is the main item which we should carry out during the modeling procedure. Elements in finite element commercial packages are divided into two main groups, as you can see in the left side of the slide. The first group of finite elements, which means that elements that we can see all variables and outputs in all edges and sides. In fact, in these elements, we can calculate the variables in all around the element, and all sides and all edges of elements are accessible for the software. But in the other group, I mean infinite or infinity elements, will be used for modeling very large parts such as soil, rail, dam, and ground. I mean, in these situations and in these problems, we have to use infinite elements, because it's very hard for the program and us to calculate the variables which are very far away from other parts. Please note that the main concern in finite element analysis is about finite elements, not infinite elements, while we can discuss about these kinds of elements in our session. The finite elements will be divided into, will be classified using three methods. In the first classification, finite elements are divided into linear or quadratic geometric order. I mean, there are two geometric orders in finite element commercial packages such as ABAQUS, and we have to know their behavior. Linear elements are very suitable for problems which experience a limited distortion, and they use linear interpolations during the analysis, while the quadratic ones are very suitable and useful for the problems for the problems which experience a higher level of distortions, and they use quadratic order when they want to calculate, when they want to integrate the variables into the elements. At the second classification, elements are categorized into three groups. The first group is solid elements, the second is shell, and the last is wire elements. In solid elements, nodes are distributed in three directions, while in shell and wire elements, nodes are distributed in 2 and 1 directions respectively. Please note that while shell and wire elements are relatively cost efficient and are very useful to produce a lower level of calculations, the solid elements produce a comprehensive gradients of variables in our models. But I have to say that solid elements may produce an expensive procedure which can make our problem progress very hard to be solved. And in the last classification, elements are divided into full integration and reduced integration definitions. In the fully integration elements, full integration elements full integration elements use a higher amount of integration points into themselves, and they can calculate stress and strain components in a higher resolution, but they produce an expensive and cost analysis, while reduced integration elements produce an effective analysis, and they are very useful, especially when we want to focus on nodal variables such as displacement, velocity, acceleration, forces, and something like that. At the end of this section, I have to say that sometimes we are not allowed, and we cannot draw a geometry by ourselves. In these situations, for example, when we want to analyze a bone, as you can see in the lower side of the slide, we have to use 3D scanner technologies to virtualize some scans from the reality part and import them into the software. Do you have any question? If you have any question, please let me know. And if not, we can go ahead. You remember?
Sorry, I have one question.
Yeah.
I'm asking about what about the accuracy solution if we use solid, for example, or shell. Is there any accuracy difference in the final solution?
Yeah, please note that solid elements are very suitable when we aim to get the precise results, but shell and wire elements ignore the element distribution during thickness and section respectively. So generally speaking, solid elements are very precise, but in some models, for example, when we want to concentrate on, for example, for example, sheet, sheet metal, in a forming progress, it will be better if we will use shell elements, because in these kind of problems, there are many nonlinearities, and they make our problem very hard to be solved. So shell elements which produce a lower level of calculations will be the better choice. But I think we have to consider many things about a problem when we want to choose the appropriate element. Okay, some problems, in some problems, it will be better if we use shell or wire elements. But solid elements is very expensive and can calculate a wide range of gradients of variable for us. Do you mean a specific problem, or you asked a general question?
For example, my major dealing with, for example, composite materials. And I tried before that when I use the shell element, it will give like more precise solution than the solid element. So that's why I'm asking why it's different in the, in the accuracy of the solution. So it's depend, as you explained now, it's depend on the I mean, on the problem. It's not, I mean, we cannot consider all problems with the same, how to say it, like with the, I mean, we cannot use the solid with all the problems, and the same thing, we cannot use the shell with the all problems. Am I right? I mean, it's depend on the nature of the problem. Am I right?
Oh, yeah. Please note that some analysis and some simulations have the better results with, for example, shell or wire elements. For example, the bonding and the lamination procedure will have the better results and precise results if we use shell elements rather than the solid ones. Yeah, it's reasonable. But generally speaking, as I mentioned, generally speaking, solid elements are the better choice in our problems. But in specific measures, as you mentioned, such as debonding and delamination, as I will discuss later, will have the better results with shell elements. Yes, that's true.
Okay, thank you so much. It's clear. Thank you. Please go ahead. Thank you.
Yeah, thank you. Thank you. Next, we have to define material model. I have to say something about material and material models. As you know, there are many materials all around the world, and most of people are familiar with them. For example, steel, wood, concrete, glass, cast iron, plastic, polymer, composite, bone, ceramic are types of materials which are very famous all around the world, and most people, whether they have academic, they have academic literacy or not, know them. But in FE commercial packages, we have to work with material models, not materials. Okay, I mean, we have to define mechanical models of material. For example, if we want to model a steel beam, we have to decide about if its elasticity behavior is linear or not, or what kind of plasticity the beam will have, or something like that. Okay. Excuse me, sir, please ask the question after the next 3 slides. Okay, I will answer the question in that moment. No problem. Please note that when we want to model a new problem, we have to decide which kind of elasticity will be occurred in our model. Okay, there are 2 types of elasticity, and the first type is linear, which is very famous, and the nonlinear type of elasticity. As you know, elasticity means that our parts will lose their deformations when we unload them. It means elasticity. the parts will be undeformed after removing the loads. Okay, but when we mentioned linear elasticity, we mentioned that the stress and strain components will be changed in a fixed rate. Okay, as you can see, the red line in the stress strain diagram show a linear change between stress and strain. Okay, it's very famous and it's a well-known behavior for a wide range of material models. But the other type of elasticity is nonlinear, which means that the stress and strain variables will be changed in different rates. As you can see, the red diagram, and there are two types of nonlinear elasticity which I mentioned in this slide: the superelastics and hyperelastics. The superelastic in, for example, SMA and shape memory alloy will never experience the plasticity and the hyperelastic or hyperelasticity materials such as rubber, foams, muscles, fats, and something like that will be used to model damping procedure, damping simulations, and used in some industrial designs. Okay. After elasticity, we almost experience plasticity. It means that the deformations will be permanent, and by removing the loads, some parts of the formations will be stored in our parts, in our models. Okay, there are four main types of plasticity, and I will talk about them in this slide. The complete elastoplastic, which means that the rate of stress will the rate of stresses will not increase during the deformation after it reaches a specific value which named yield stress, as you can see the purple diagram in this photo. Okay. The classic elastoplastic, which is the well-known and the famous and the most famous behavior of plasticity, means that the stress and strain variables, the rate of stress and strain variables will be decreased after the diagram reaches to the amount of yield stress, and the stress values will not never grow up after it experiences ultimate stress. As you can see, the green line mentions there are two factors of plastic stresses in our model. The two definitions are very useful and very and very famous for ductile metals. The Johnson-Cook definitions, the Johnson-Cook definition is a new definition of plasticities. It mentions that the behavior and the stress-strain components of materials depends on the rate of stress, the rate of strains. It means that when we, for example, when we compress some parts with different rates, the beam experiences different levels of yield stress and ultimate stresses. So the material model is very useful when we want to model impact, explosions, and other dynamic procedures in our model. The final plasticity model, which is very useful and very famous among FE commercial packages, is concrete damaged plasticity, which in that material model we will be able to model some brittle materials such as concrete, because these kinds of materials have different behaviors when they put under, for example, a compression or tensile loading. In that plasticity definition, we can define different compressive or tensile behavior in our model, and it's very useful to model all constructional materials such as cement, concrete, soil, brick, and something like that. And finally, we have to define items which define the damage behavior. For example, if we want to define crack, we have to input some data which implemented on the maximum, for example, maximum principal stress which the parts can undergo. And when we want to define erosion, corrosion, delamination, fracture, and fatigue, we have to define the corresponding data in the model. Erosion is kinds of damage, is a kind of damage which take place when some parts are in contact with each other and have a a relatively higher level of friction, and the corrosion will be carried out, will be occurred when the parts are in the vicinity of chemical mediums. Delaminations and debonding is a kind of damage which takes place when we bend a plate, a delaminated composite plate, and some plies are damaged due to the pass of ultimate stress, and fracture and fatigue are other kinds of damage which we have to define the corresponding data for them. After that, in the third at the third step, we have to define the analysis step. There are many classifications of steps which I say something about the main two classifications at this slide. The main category, the main classification is time dependency. It means that analysis steps are divided into two types based on time, based on their time dependency. The time independent problems are the problems in which we can ignore the impacts of accelerations in our model. It means that in those problems the structures will not experience changes during the simulation. For example, structures are under their weight can be analyzed in a time-independent protocol, and time-dependent problems are divided into two main groups. The first group of time-dependent problems are the problems that in which the problem situation depends on the time and will be changed during the time duration, but the impacts of acceleration can be ignored, so they can be considered statics. For example, a pedestrian's movement when they walk, for example, on a bridge, will produce a lower level of acceleration which can be ignored. But in the other group, the time-dependent problem, the time-dependent problem include a higher level of accelerations. For example, in earthquake phenomena or in impact problems, we are not allowed to ignore impact and acceleration effects in our model. At the other classification, the procedure type will be divided into two types, the linear procedure and the non-linear one, which in which a higher level of calculations will be occurred in non-linear problems, while the linear problems are cost effective and can be modeled easily. So we have to decide if our problem should be analyzed in a linear aspect or in a non-linear scheme. Okay, please let me know if you have any question from these slides. Okay, whether the size of the meshing of each element is very influential on the solution. Okay, please note that we can check the mesh independency if it's your question. We can check the mesh independency in our model by considering a lower size of elements in our model. We can examine our model by a lower size of elements and check the results in a specific region which we aim to. Okay, after some analysis with a different size of elements, the results will be converged into a unique value, and it means that after that the values cannot be changed by considering the smaller mesh size. Okay, but please note that in some situations there is a round-off error. The round-off error is that the amount of solution will not be converged into the unique solution by considering the smaller element size. I think in that situation we have to customize the process, the analysis, the procedure of analysis, and prevent the round-off error. Okay, is it your question? Hello, are you there? Did you get the answer, or you have other question? Okay. I mean, for me, there is no. Okay. Thank you. Okay. We can continue to the remaining slides. Okay. After that, we have to decide about the defining circumferential conditions. I mean that we have to define our parts behavior with the other parts. There are 5 items which should be considered when we want to define circumferential conditions. First of all, we have to take care about loading protocol. I mean, we have to define the loading protocol as well as possible. Loading means that anything which excite our structure. Loading can be load can be force or heat flux or acoustic impedance or something like that. In structural problems, we face with many form of force as the loading. For example, point force or concentrated force, edge force, distributed force or pressure, body force, and something like that. But in other kinds of problems, there are other loading, such, for example, electrical potential, heat flux, and acoustic impedance are kinds of loading which can be defined in the program. Then we have to define boundary conditions. Boundary condition is specific changes of degrees of freedom in certain regions during our simulation. I mean that we have to define the changes of degrees of freedom in some specific regions of our problem during the analysis. Okay, and please note that the more boundary conditions and the more regions which have the boundary conditions, the lower size of calculations and the higher speed of solution. Okay. But in some problems, it's not very easy to realize the boundary condition. Okay, but while in some simple problems, like such as the problem you can see in this slide, it's not very hard to realize the boundary condition. Okay, for example, if we want to simulate a human body, it's not very easy to define boundary conditions. But in a, for example, in a cantilevered beam or in a in this beam, it's very easy to realize the boundary condition. Okay. Then we have to define interactions. Interaction means defining the method of interacting or interactions between parts based on the simulation process. As you can see at the bottom of the slide, there are 2 beams which are placed with a clearance. In fact, the clearance can be disappeared if the upper beam experiences a a large amount of load. Otherwise, the upper beam cannot fill the gap, and the upper beam will not reach the upper beam, the lower beam. Okay, so interactions depend on the problem situation, and we have to it's not very easy for users to predict what will be occurred when some parts are interacted to each other. Friction is the general and the most famous definition of interaction in structural problems. Next, connectors, which are predefined mathematical connections between different vertices of parts. Okay, for example, if you aim to define a suspension system, vehicle suspension, you have to define some, for example, linear or non-linear spring, dashpot, stopper, and something like that. So in these problems, connectors are very useful and help us to keep our problems as cost efficient as possible. And the last one is initial condition. Initial condition, the predefined condition of the problem before beginning the analysis. It means that the situation of our problem in time zero. Okay, for example, the speed of impactor, speed of an impactor when it reaches to, for example, platform, okay, V0, or the initial state, or the initial temperature. Okay, there are examples of initial condition which after that the analysis process will be started. Okay, the fifth step is about requesting outputs. In this slide, I defined variables. Variables are whatever can be varied during the analysis. There are two main groups of variables. The dependent variables and the independent ones. The independent variables are the variables. The dependent variables are the variables which can be calculated according to the invariant variables, to the independent variables. I'm so sorry. There are two independent variables, time and frequency, and other variables are dependent variables. Okay, so I mean a dependent variable in the course. Okay, the dependent variables are divided into two main groups, the nodal variables and elemental variables. Okay, the nodal variables are calculated on nodes, such as, for example, acceleration, displacement, rotational displacement, reaction forces, concentrated forces, reaction moments, concentrated moments, and velocity. They all have to calculated unknowns. And the elemental variables are calculated on elements and integration points, such as ALL, which mention to energy components, S as stress components, E as strain components, EE as elastic strain components, PE as plastic strain components, EQ as equivalent plastic strain, and something like that. Okay, but we have to define outputs. A reasonable arrangement of variables. I mean, a reasonable arrangement of dependent variables. When we arrange the dependent variables, we can reach the goal of the problem. Okay, goal of the problem is extracting the outputs. There are two main output in FE commercial packages such as ABAQUS: the fill output and the history output. The fill output means that if the variables, the dependent variables, are sorted by value and distributed on the whole geometry, as you can see in the figure. For example, it's the stress contour plot, and it's a kind of fill output. All stress variables are sorted through the geometry, and we can see which part of the body experiences a higher or a higher level of stresses. As you can see, the upper and the lower side of the whole, and which part experiences a lower level of stresses. Okay, and the history output, the history output means that if the dependent variables of a specific region are placed together during the analysis. Okay, if we extract some variables and put them and arrange them during the time, we can access the X time plots or history output. Okay, please note that the fill output mentions in fill output we can see all variables in our model, but in the history output we can see the change of variable in just one specific region of our model during the analysis time. Okay, and finally we have to define a job. A job definition includes subroutine files directory when available. Decide about restart or full analysis of the model. In addition, we can decide about the allowable physical memory for our analysis. I mean the accessible RAM, physical memory, and we can determine the precise level for ABAQUS explicit solver, which I explain about it later, and something like that. It's the final step of the modeling process in ABAQUS. And after that, we have to submit our model to be solved by the program. Please note that all the progress can be carried out in ABAQUS CAE program as the main GUI program which is available in ABAQUS package. Okay, the program is very user-friendly and have a powerful GUI which help users to conduct their problems step by step, and they can review their model easily. Okay, if you have any question, please let me know. Vortex, do you mean fluid flow simulations? Vortex or vertex? Oh, if you mean a turbulence simulation, yeah, do you mean turbulence simulation? Oh, please note that the course is a basic one, okay? And I have to say that I'm not expert in CFD analysis, okay? I'm a super advanced user just in structural problems, but not CFD models. I think this type of problems are very complex for me, and I cannot simulate them. Okay, but I did them. I did a vortex and turbulence fluid flow before, but I think it's very hard, and these kinds of problems are very complex, to be honest. Okay. Can you send the recording of the yeah, why not? Don't worry about it. Yeah. The recording will be accessible for all participants after the session. Okay. So I have to say something about the products which are available in ABAQUS package. The main product is ABAQUS CAE, as I said, the complete ABAQUS environment, in which users can conduct and can model their problems easily. After that, we have some solvers. The main and general solver of the ABAQUS package is ABAQUS standard solver, a general purpose find element solver that employs implicit integration scheme, the traditional progress, based on unconditional stability method. I mean that in this procedure, the program try to find a solution to the nonlinear system of equation iteratively by considering the current state of the system as well as its subsequent time state. The solver is very famous all around the world, and there are many problems which can be analyzed with the solver. For example, frequency extraction, buckling, nonlinear solution, nonlinear static problems, heat transfer, coupled temperature displacement problems, acoustic problems, soil consolidation, and other problems can be simulated with the solver easily. But please note that the solver is relatively expensive, and it needs to form matrices to solve the problem. As you can see at the bottom side of the slide, there are, for example, there are a system of equation with 4 variables. X plus y equals to 1, y plus z equals to 2, z plus w equals to 3, and w plus x equals 4. Okay. The solver will form the matrix of multipliers, matrix of variables, and matrix of responses. Okay, and to solve and to obtain the variables, the software tries to inverse the multiplier matrix and solve the problems. Okay, because of the unsymmetric matrices, unsymmetric matrix, and a wide range of equations to solve the matrix, the procedure is relatively expensive, and for a higher level of elements and complex behavior in our model, it's not recommended to use the procedure. Okay, the matrix are coupled, and the couple of the equations prevent the program to have a efficient and to have an efficient calculation. Okay, and this is why the ABAQUS package has another solver. As you can see, ABAQUS explicit is a special purpose find element solver, not a general purpose. Okay, a special purpose find element solver that employs explicit integration scheme to solve specific problems. Okay, based on conditional stability method, not unconditional stability method. Explicit dynamics is a time integration method used to perform dynamic simulations when speed is important. As you can see, it's explicit dynamics. So explicit is a kind of dynamic problems, which the acceleration is very important in them. Explicit dynamics account for quickly changing conditions or discontinuous events, such as free falls, high-speed impacts, and applied impact loads. As you can see in the GIF at the bottom of the slide. Okay, in this solver, the state of the equation will be converted to other equations and form a new form a new system of equations which are not coupled to each other. In fact, in this solver, a new system of equations will be provided in which all variables can be obtained independently from the other equations. As you can see, the four equations were converted to a new four ones in which each equation can be solved independently and it don't need to other variables. So the solver is very sufficient, is very useful for problems in which complex nonlinearities and high-speed events are available. Okay, and the next program, the next solver in ABAQUS, which is presented in ABAQUS package, is ABAQUS CFD. I'm so sorry. CFD solver. A computational fluid dynamics solver which provides advanced capabilities with extensive support for pre-processing and post-processing. Computational fluid dynamics is the analysis of fluid flows using numerical solution methods. Using CFD, you are able to analyze complex problems involving fluid-solid, and fluid-gas interaction. Please note, I'm familiar with the solver, but I have lower experience with it rather than the two formers. Okay. As you can see in this solver, we are able to model fluid effects, fluids and fluids and their effects on another, for example, solid or fluid parts. Okay, please note that there are many there are many methods to define fluids in ABAQUS. Okay, CFD is one of the popular and precise method to define fluids, but we can use CLE, coupled Lagrangian-Eulerian method, or SPH method to define fluids in ABAQUS. Okay. Computational fluid dynamics (CFD) is the analysis of fluid flows using numerical solution methods. Okay. And now the session. The first session of the free online course will be finished. Okay, we can use the remaining time to speak with each other about your problem and about whatever you think it's better to talk about that. Okay. Please let me know if you have any idea about your problems about your models and something like that. Do you have any question? You can speak, no problem. You can speak with your microphone. Okay, what about carbon fiber reinforced polymer? How can I represent it? Okay, please note that if the polymer is very thin, okay, and the thickness can be ignored rather than the other dimensions, it will be better if you use shell elements, okay, shell elements. But please note that in this definition, the carbon fibers should be detectable, okay? The separated fibers, I mean. Otherwise, you have to define orthotropic or anisotropic material definition in model. We can speak about it and discuss about it in the next session, And for the glass fiber reinforced polymer, we can I will discuss about it at the next session and show you some tools and items in the program. Okay, but please note that fibers can be modeled in two main different methods. Okay, the first one is when the fibers are separated from each other. For example, the first fiber, the second one, the third one, the fourth one, and their distances are represented. Okay, but if fibers cannot be detected, okay, and they mixed and they are mixed with the host, you have to use anisotropic and orthotropic material definition. Okay, now we can talk about it at the next session. Okay. Other question? No question? Okay. I finished the first session of the free online course of ABAQUS. At the next session, we try to simulate a simple problem in the program, and you can ask some question about modeling techniques and something like that. Okay, have a nice day and goodbye. Please note that you can download the recording from the chat room. The recording will be available in the chat room when I finish the session. Okay. Have a nice day and thank you and bye.